Good day, everyone, and welcome to NDT Talks, where global experts come together to explore the technology shaping the future of inspection and safety. Today, we are diving into a subject that sits right at the intersection of innovation and safety: eddy current testing and how it helps high risk industries operate smarter, safer, and more efficiently. But before we begin, a quick reminder: if you haven't yet checked it out, One Stop NDT recently released the Robotics for Confined Space Inspection Buyer's Guide 2025. This exclusive guide helps you understand how to choose the right robotic solution for safer, more efficient inspection in hazardous or limited access environments, with expert reviews, technology comparisons, and field insights. You can download it right now at onestopndt.com. It's a must read for everyone who is involved in inspection planning, operations, and asset integrity management. So it's always exciting to see how global and diverse the entity community truly is. And with that, let's meet our fantastic lineup of panelists who will be sharing their insights today. Mr. Alexander, Chief Founder and Managing Director of Probe Inspection FZE, with over 15 years of hands on expertise in eddy current testing of wells across ferrous and non ferrous steels, known for his precision driven fieldwork and practical understanding of ECT probe technologies. Alexander brings deep insight into surface flaw detection and signal interpretation. Mr. Mirbek Musatayev, a researcher at the Civil Aviation Academy, Kazakhstan, whose work focuses on NDT and automated fiber placement technologies. He recently completed his PhD on developing directional eddy current probes under guidance from the University of Bristol. His expertise blend academia, innovation, and real world aerospace applications. Dr. Ronnie, a distinguished veteran with over 24 years in NDT, spanning military, aerospace, and industrial sectors, a US Marine Corps veteran and co owner of Paradigm for Excellence. Dr. Ronnie brings unmatched experience in leadership, workforce training, and applied inspection technologies across organizations like Pratt and Whitney, Lockheed Martin, and Gulfstream Aerospace. And leading today's discussion is our moderator, Mr. Dheeraj, Principal NDT Engineer at Oceaneering. With over a decade of global experience across oil and gas inspection operations, Dheeraj is an IIT Kharagpur alumnus and holds ASNT and PCN Level 3 certifications in 10 NDT techniques, including eddy current, ultrasonic, radiographic testing. He is known for his deep technical authority, mentorship, and leadership in integrating advanced inspection solutions into asset integrity programs worldwide. We couldn't ask for a better mix of expertise for today's conversation. So let's move on to the session. Mr. Dheeraj, over to you.
Thank you, Gary. Thanks a lot for the great round of introduction. And I think the way you have mentioned, we have a very extreme, diverse set of expertise, and very pleasure. And it's I think a great occasion to lead such a panel. And I think let's not keep people waiting, and let's jump into the topic of today. So we are going to discuss one of the key important topics, which is eddy current testing. As most of us know, NDT people, ultrasonic, radiographic, eddy current, and so many other techniques are very vital. But today we are going to discuss how eddy current testing can boost safety in high risk industries, right? And most of us are working in pretty high risk, let it be oil and gas, aerospace, or medical, right? And predominantly in oil and gas, we use eddy current a lot, in aerospace as well. So I think it's going to be a great round of discussion, right? So to not let the panelists keep waiting, and as well as the audiences, I'm going to jump in with the first question. Let's start with the plain and simple topic, right? So when do we think eddy current testing actually made people safer in your world, for the panelists, right? One specific story, probably, if you could recall, or one of the fond memories of eddy current testing, where you caught some defects early on and it changed your decision, and what could have happened if, let's say, you didn't catch the defect, or if it went unnoticed, or during a turnaround or shutdown, if it made a drastic decision change, right? So if you could recall, probably starting with Dr. Roni, if you could recall one incident where eddy current testing really changed the decision making in your world.
Okay, good morning, everybody. Okay, well, like I said, I've worked a lot of aerospace, and recently, last year I was working at Virgin Galactic, on the space shuttle that they have, and I also had interview with a job at
Yeah.
SpaceX for Eddy Current inspection that they said I was just overqualified for. But, but other than that, it was good. But I definitely think that, especially when you're looking at right now, it costs so much for its hazardous materials when we have to strip parts and things like that. Believe me, that is not only is that dangerous. A lot of people end up getting skin diseases and things like that from using the high-powered strippers that we use to take the paint off metals, and then sometimes the paint will even go so far that it'll remove, protective coatings as well. So when you can have eddy current used to replace those harsh, because like whenever you use ultrasound, 9 out of 10 times, or probably 99 out of 100, you have to strip the whole part, and then even with that, setting up for ultrasound can be very, very complicated, based on the various metals and their effects on sound and how deep and how far you can go. With eddy current, to me, is a much simpler setup. It's safer and it's actually faster, much faster. But I don't know if it's because, like, one of my biggest reasons why I kind of went from being a technician to more of a management specialist is I just feel that a lot of times in the field, our level threes are not doing enough to create new inspections with new techniques. What we usually do is we'll take the initial inspection criteria and we just keep on running with it. When there's a lot of cases where we could do another method that actually is better and more accurate than what we're doing. I just feel that a lot of times the level threes attach so much with just doing the technical work that they don't get into the real management portion, which is not only managing your people, but also managing your equipment, your techniques, trying to stay up on what's the newest equipment that's out there. There's been so much that came from. I remember when I first started NDT, I think I went to NDI school in 1986, and we had this machine called the NDT 25. That thing weighed 60 pounds. you know? Now we have things that you can hold in your hand that does 10
Yeah.
times what that machine did. So I don't think we're doing enough in the field to continue to grow and make the inspections better. And I definitely think, as far as getting rid of stripping materials, that eddy current brings so much to the table.
Great. I think that was a great, inspiring kind of a background you had with eddy current testing. Great to know that it really, helped you a lot in aerospace. Probably if we could move on to Mr. Murbik, like how about your experience with eddy current testing and any, classic examples or cases where it was really, world changing for you?
Hi, everybody. Thank you for organizing this event. Yeah, as I introduced myself, I was studying my PhD during my placement at FINE CDT, Future Innovations in Non-Destructive Testing at Bristol University. So, being a curious student of material science, I once joined a colleague session at UNDT, our lab. So it was focused on detecting some out-open wrinkles on L stiffeners corners. If you know, these L stiffeners mostly
Yeah.
used for airplane wings, for example, to provide some strength. That challenge really caught my attention, and I couldn't sleep that night. Honestly speaking, I was thinking how we can adopt our directional eddy current probe for this challenge. So basically, because of our receivers has winded in differential mode, we decided to place two receivers across the corner to inspect the L stiffener. So this decision was crucial because the results were striking. We could detect some out-open wrinkles early, so it became not a structural concern. So this particular example was something that I recall from my memory. And as you know, this out-open wrinkles is reducing the compression strength around 30%. So this is kind of a crucial thing. So we are now concentrating how we can publish these results. Yeah.
That's a great, innovative kind of story. I mean, I think that's it's a kind of a weird, bit crazy application, right? So when we see how we are going to apply NDT technique, and especially the case where you said about stiffeners, it's going to be a classic case for eddy current testing, right? Other techniques are going to be like quite not competing with eddy current testing, and glad to know that particular example. Thanks for that. And Mr. Alexander, how about your inspirational story? Probably some world changing and kind of mind blogging stories on eddy current testing. Yeah.
Yeah, gents, thanks very much for having me on board. And apologies for the lateness. I had to skip for prayer times here in Dubai. So, um, thanks for waiting up and for accommodating me. Yeah, so my name is Alexander, as you can see on the meeting line. I'm based in Dubai. I've been doing NDT now since 2011, precisely. And I'm ASNT NDT level 3 and 5 methods. I do a lot of work in the oil and gas industry, primarily oil and gas upstream, so drilling industry, onshore, offshore. So my most exciting foray, I've been doing mostly standard weld inspections all these years. High strength low alloy steels, both onshore, both offshore mostly, and then standard mild steel to high alloy steel onshore. Uh, two scenarios come to mind when it comes to my eddy current experience. One had to do with so in the drilling industry, if any of you are aware, there are these special components that they use as you go closer to the bit, the drill bit. So they have these special tools. They call them bottom hole assembly. And some of those tools are non-mag in nature, non-magnetic. So austenitic stainless steel and martensitic stainless steel. Martensitic is a bit magnetic, but austenitic is not. So I had to do some work back in Qatar in the day in 2014 or 2015 thereabouts. We were looking for stress corrosion cracks. LPT didn't quite work the way they'd hoped, so I had to step into. I was using a FASEC system, it's a digital system, impedance plane display, and absolute probe configuration, basically bridge type probes, typical usual frequency 100 kilohertz or 150 kilohertz. And so using that, we're able to both find and get some degree of quantification, although we later on had to rely on slightly advanced penetrant testing, something as basic as penetrant testing, to get more quantification data, kind of an estimate. So that was the first foray when it came to something exciting in the eddy current space. The second was and has been offshore, specifically for jackup rigs. So we do a lot of underwater inspections. And my specialty nowadays is mostly underwater eddy current. So doing inspections on underwater high strength girder wells, TKY joints basically, and we use ROVs for those ROVs. So I use a pretty advanced and custom system called Sensima. The company is based in Switzerland, and they do a lot of research. They've done a lot of research for underwater probes and the accompanying software, impedance plane software, which is quite intuitive. So I've had some good success in detecting quite a number of cracks actually using the system underwater. Standard. So they have two kinds of probes. So absolute probes again. Absolute. So basically, we're looking at bridge differential, one of them, and then bridge probe. These two. Average scanning frequency of about 216 to about 250 kilohertz, approximately. So yeah, so that's been the story. It's been exciting and still ongoing. So I'm doing a lot of work in that area right now, and more findings, and then we feed them back to our partners in Malaysia and to Switzerland. So yeah, that's my story in eddy current testing, and I look forward to having a very constructive evening. Thanks, gents.
Thanks a lot, Mr. Alexander. That was very inspiring. It's all the way in subsea. We heard like a couple of things from aerospace. You took us, below sea level. That's exactly where kind of I work with oceaning as well, more subsea and ROV stuff. Really exciting. Eddy current is something which we can use all the way from like space to all the way to subsea, right? It has like intricate applications everywhere, and I think the diverse panel has proved it in the first kind of discussion as well, right? Like starting from stiffeners, aerospace components, till subsea components, all the TKY joints and the structural wells. Yeah, it's very diverse applications that are there. So I think it was an exciting discussion. So let's roll on with kind of a second round of discussion on when ECT is and isn't the right tool, right? So to put some context more to it, let's say for a plant or an asset inspection, when dealing with a manager, right? How do you explain when ECT is the right choice and when isn't? To be more precise, if you could quote one example where you choose ECT over other NDT technique, and other classic example where you said, no, this will not be ECT, let's go with some other NDT technique, right? So if you could give two examples where it was a go for ECT and no go for ECT, that'll be great for the audience, I guess. Yeah. Who wants Ronnie? Dr. Ronnie, do you want to go first?
Okay. Well, let me give a little bit. Like in aerospace, a lot of people be surprised at how many things we use ECT on. Like, how many did you know that whenever an aircraft has a lightning strike, you have to do a conductivity test on a material to see if it's lost its properties? Believe it or not, I've seen cases where a lightning strike took a metal from, say, a T1 strength to T3, which can mean it's now too brittle to do its job. And also, there's a lot of cases where in penetrant, you have to acid etch things. Like, say something has too much, say you have a crack and you end up blending it or whatever. And so what happens is, as we know, whenever you grind a sand metal, it actually smears the metal. And so for now to be able to be inspected, a lot of times you have to have what we call acid etch, but you take an acid solution to clean it out. And often, so when I worked at Gulfstream, they use a lot of Rolls-Royce engines. So whenever you had a case where, and then the thing was, a lot of facilities do not like to use acid, so they don't have the capability to do acid etching. So you always ended up having to request permission to do eddy current, because eddy current will go right through the smeared metal and things like that. But to me, I'm like, well, why don't you just make it an eddy current inspection? To start with, and have to go through all of these, because usually you got to write them a message, explain everything, why you had to do why you had to grind it or whatever, and now it's been smeared. When it's just, to me, it should be in a lot of cases, because most units have an eddy current set of eddy current machines, but we end up wasting a lot of time and effort getting an approval to do something that's pretty, really simple. Come on, the eddy current is going to pick it up if it's cracked, whether it's got smeared metal or not, but we have to go through that process. And then, like I said, for its conductivity, it's really amazing how well eddy current can measure conductivity of a metal. And like I said, some people may not realize how important that is, but it could be a difference between a metal being too hard, too brittle. And now when you have a plane riding through the atmosphere and, it's going, 180 miles an hour or whatever, believe me, it makes a big difference. And so, but a lot of times companies like to go the cheapest method. And that's why a lot of times you'll see there's a lot of penetrant inspections out there, not because the penetrant is a quality inspection, but because it's usually the most affordable for a lot of companies, and so, and I would say that even now, maybe that was a time when a lot of eddy current machines were very, very expensive, as the technology increased, but I'd say they're completely comparable to, and in most cases, a lot of them are cheaper than UT units. And then if you look at X-ray items, well, you're going to save a lot of money there and get just a quality inspection. But a lot of people like pictures. So like right now, I'm a QA at a nuclear plant, and they make nuclear fuel. And so when they encase the uranium in these cases of metal, they have to have what they call homogeneity, and it has to be smooth all the way across so that you don't have too much radiation on one side and one on the other. And they also use X-ray to verify, that, and they rarely use eddy current. So when I got to the plant, I was like, why don't we have any eddy current applications? They say, oh, well, we just use X-ray. And so I'm trying to work with them to see if we can find some more eddy current, because once again, it's much safer, cleaner, faster, and I think more reliable. Because we all know X-ray, depending on the quality of your radio, you can, and if you're not shooting in the exact right spot, you can miss it entirely, right? So, but trying to educate people on that sometimes can be a challenge, because they go, oh, we can get a picture. It takes a lot to get that correct picture. For as an eddy current, we have ways of recording defects now. We have ways of comparing good to bad all on one screen. So it definitely needs some more education on the public's part. The only place where I see that we have had some problems where we couldn't do eddy current in some spots where I felt we should was mostly because we didn't have a lot of adapters. Like we didn't have enough probes that were created the correct way to get in there. So I definitely feel in the field, we need to get more extension rods and things like that in there. Could probably increase our space to get into some tight places that a lot of people, oh, well, you can't get in there, so we got to do an x-ray. And really, x-ray is sometimes a hit miss. You know what I'm saying? But if we can get that
Right.
probe in there, we can get on the spot. We can get a great
Yes.
picture. We can compare it to a good sample and so on. So those are some of the cases where I think it's kind of hard when you're trying to make people understand that, yes, UT and radiography are certain, but they can be very complicated and they can miss it more often than not, what you're looking for. At least that's
Yep.
been my experience.
Yeah, that's a great couple of examples you mentioned, right? Sometimes, probably especially for people who are very commonly using X-rays or radiography, ultrasonic, sometimes to just use it, it may be a comfort zone, but it may not be the right application. You exactly like nailed it on the spot. And thanks a lot for giving examples for both cases. Alexander, do you want to go next? Alexander, you're muted.
Yeah, that's right. So yeah, it's on. I unmute myself. That's right. Yeah. So like the two examples I gave you just at the start of my intro, the one the one that was in Qatar actually. So that was a non-magnetic specialty tool. Actually, choice was penetration testing, like Ronnie just said, price. I mean, it works with the correct procedure and well, but then price was the main thing.
Got some network issue, probably. Okay, so Mr.
That's
Alexander,
weird. Just kind of jumped on me.
oh, we got you back.
Yeah.
Yeah.
Can you hear me? Yeah.
Yeah, it's loud and clear. Yeah, you can go ahead.
Yeah, that was weird. It just jumped on me like that. All right. Yeah. So, anyways, yeah. So the choices between was basically penetrant testing, but then supplemented by eddy current, kind of a play. And so we went for eddy current because okay, we could do it. That's the first thing because training is an issue. Now, Ronnie's not from Ronnie's perspective, from what he's saying. I take it that his experience vis-a-vis some of the folks in the US has made it easy for there to be some kind of understanding and knowledge, knowledge sharing in this area. But in the Middle East, where I'm based, the electromagnetic techniques still pretty much a challenge. People don't quite get it. They're still struggling with the basic physics of it and all that stuff. So if you're having those issues, then you've got probe selection problems and things like that, which is, it's a non-starter. So my company happened to have the personnel, myself and a few others who could handle it. So we went in, got it done, and yeah, it was pretty easy because, especially for non-mags, it's quite easy. And it's a fairly spherical, it's about 9 inches OD component, so pretty, broad radius. And the pros we had also had good, nice curvature, so there was good coupling. And once you have sufficient coupling, then it becomes a matter of scanning and interpretation, especially if the procedure is well crafted. So yeah, eddy current to swap in for eddy current for LPT, but then LPT was used again to kind of supplement or complement the sizing because it was basically it was a cluster of stress corrosion cracks because of high sulfur, a very, very high sulfur rich well. I think that was more than 3,000 meters deep at the time. So high temperature, high sulfur. So yeah. That was one. The next, and that was a phase X system. Now the next, underwater MPI versus eddy current testing. As you all know, gents, as you all know, the debate is between MPI versus electromagnetics. MPI is part of it, but MPI is sort of more physical. So MPI always wins if it's ferromagnetic and you can access the area clearly, and you have the time and they can remove the paint and things like that, and cost, of course. But in some instances, to get the paint off and all that stuff, not quite easy. So you got to go for eddy current testing. So underwater MPI is quite expensive for those who, if you have any awareness. I think Mirbeck and Ronnie, it wasn't aerospace. So in the oil and gas industry, it's It's not that clean. It's pretty it's cowboy territory, quite rough, if you know what I mean. So underwater MPI is quite expensive because divers, you got to send a diver down there and things like this. So eddy current definitely. Also from a cleaning perspective, underwater marine growth, depending on how old the platform or the rig is, or the barge, or the floating production vessel, because they use them also on FPSOs. This large, fuel storage tankers or production platforms. No, not a platform. It's like a barge versus a platform, kind of in between. It's like a drill ship, you can say. So sometimes the marine growth on these can be so difficult that even at 3,000 psi or even 3,500 psi, cavitation gun blaster, you still can't get the marine growth off. So switching for a 10 mm probe unshielded, unshielded bridge probe, to a 40 probe that big, because we're looking at very large, minimum 2-inch wells. These are quite big. So switching from that narrow probe to a pretty broad probe, you can have a very strong magnetic field, even with more than 5 mm thick marine growth and with roughness as well. So switching to that, you can still get good detectability and good discrimination, good resolution, so to speak. So we basically use that to isolate, signals from the background noise. And yeah, so many times we've had to convince the client to go for eddy current testing. It's a bit more expensive, but overall cheaper if you look at the whole arrangement for getting underwater MPI done or dry docking done. So yeah, that's my 2 cents. And yeah, thanks.
Yeah, thanks a lot, Alexander, for bringing in the subsea perspective. It's great. I can totally correlate to it, been working on that oil and gas platforms and stuff. Mr. Murphy, do you want to add your... Oh, sorry, Mr.
I got a question. Got a
Oh,
question.
yeah, please go ahead.
Alexander, like now a big thing right now in aerospace is the immersion testing with UT. Do you think there's
Yeah.
some applications where we can use the MPI, like you said, to replace some immersion testing?
So typically immersion testing thin parts usually. So in general, now in your case, I'm guessing what's the average thickness and the material? So ferromagnetic steel, number one, yeah.
Yeah, less than an inch.
Or
It's less than 1 inch.
less than 1 inch. How big? How big is the part? Like overall area and the
Uh,
shape and stuff.
I'd say maybe from one to, I'd say the biggest we probably doing is maybe say 3 feet, maybe 3 feet, like doing an entire longeron, and pre-manufacturing applications. So yeah, right now we're just putting them in tanks
So
and
that's
robotically doing UT.
all right. So half an is about half an inch. You say half an inch or thick?
Yeah, between a half an inch and max is an inch of
Cool.
thickness. All right. So say a stringer, entire stringer so when we're building
Okay. Well,
aircraft,
in that case,
we do a UT
you
immersion
wanna
of all of those
because
longerons and stringers
underwater.
before we
Okay. Is it my internet connection? This is weird. Just one second, guys. I don't know if I'm having some kind of interference issues here. All right. Can you hear me?
We got you
Yes, I
back.
can.
All right. Yeah. So yeah. No. So Ronnie, in your case, I think you want to stick to immersion UT because if done to a proper procedure, it's quite accurate, and you already have the fixture in place. So if you're looking for both surface and subsurface, clearly, yeah, immersion UT,
UT is
because
better.
already your dead zone is taken care of. So which means surface
Yeah,
resolution is quite to begin with. You could pretty much capture stuff, very close to the outer edge. But alternatively, if so, it's aerospace. So AC will work, of course, for surface floors, DC or half-wave DC for both surface floors and subsurface floors. If you want to preserve the finish of the component, meaning the actual finish for the you said manufacturing stage, because if you want to preserve the finish, then again, immersion UT. Because the only option for MPI where you could find even subsurface floors, which is the main purpose of UT, would be prods. You're gonna have to use prods. But the problem with that is that you have the basically scalding, not scalding, hardened spots. You're gonna have arcing on the surface of
right.
your test piece, and so yeah, so
Yeah.
immersion UT definitely. If I
Okay, thank you.
understood your question correctly.
No, that makes sense. I was just curious. There's some other applications you know.
Yeah.
Because I can certify people a little bit quicker for MMT than I can for UT in some cases.
Oh yeah, no, yeah, that's right. That's absolutely right. That's for sure.
Yes, sir.
All right.
Yes.
I think that's a great question, Ronnie. But a quick jump on the other side. But yeah, it's a totally new application. And thanks, Alexander, for that. Over to you, Mr. Mabik. Do you want to add your view on the eddy current testing? Like, where, like, kind of, you said no for eddy current testing, and yes, for sure, this eddy current testing has to be used.
Yes, thanks for this question. I don't have so much experience as our respected experts in eddy current testing, but based on my experience, we focused on two different types of applications. One is for rail inspection, and another one is for AFP, manufacturing process inspection. So both of them are dynamic tests, as you know, and why we choosing eddy current testing among other NDT methods, primarily because for first application in rail inspection, for example, when you are dealing with a high speed, for example, all of these train-based inspection systems can go up to 50 kilometers per hour. For example, for 30 kilometers per hour, ultrasonic inspection technique used heavily in this direction has limitations. It can only detect defects up to 4 millimeters in depth, which is so eddy currents can do at high speed with high accuracy, reliability, and also we can detect some early detection of cracks such as rolling contact fatigue and mostly smooth. I don't know, maybe you hear or not about this kind of defects types. Also, another application what we dealing with is automated fiber placement manufacturing. Ronnie, I think, should know about this application where you are applying some tapes. So you are applying composite tapes by applying some pressure by a roller, and also you have a speed and a temperature. So temperature goes around 40, 60 degrees by Celsius for thermoset materials, and the speed normally goes below 1 meter per second. But this kind of application requires some, from currently used laser profilometry and the thermometry struggles because, it can only measure the top surface inspection techniques. And this is a top surface inspection techniques. When you are not having some profile change, for example, in-plane waveness, cannot change the profile, but eddy current testing can do it better because you are eddy currents tend to flow around the fibers. So these all unidirectional fibers, and when some misalignments occurs, eddy current can do it better rather than profilometry. And the good news is the thickness of the layer is around 0.31 millimeters. So this is kind of I think another good example of eddy current usage.
Yeah, that's a great. Thanks for bringing in the rail perspective as well. That's I think totally out of the world and kind of a diverse experience. We could glad to hear of that. So I think it's going very interesting. So I'm gonna put like kind of question which is going to I think raise eyebrows off. So trust and clarity when it comes to eddy current testing, right? So what proof typically makes you comfortable making eddy current call? Like as NDT experts, we all know, right? Whenever a technique is used, whether we are confident on it or do you want to use an alternate technique? There are a lot of questions always, right? For when it comes to eddy current testing, what makes you confident? Is it like the calibration reference blocks, the tryouts, validations you do on known samples, right? Mock-ups, second eye reviews by some experts, or the trend history based on the past records of inspection or so on. So what gives you confidence to go back to your leadership and say, I'm 100% sure on this because of so and so reason? So what is something which you typically rely on to get the trust and confidence on the eddy current testing? Mr.
Well, it all comes back to the reference standard, can we find the defect that we're looking for? And then, like I said, what usually, like you said, like Alexander was saying, everything these days is based on cost. So it's what does it cost us to get, what we're looking for? And like I said, I felt that in many cases the Eddy Current was most economical, and I had the most confidence in using it. So we had situations where, like, okay, like in the space industry, like with SpaceX, like I said, I worked at Virgin Galactic for a while. We got to realize a lot of these inspections never been done before, and you would think that they would borrow a lot from like aerospace, but unfortunately, my experiences was they really didn't. They really just like tried to just reinvent the wheel every time, you know. So there was a lot of new things that because a lot of things they didn't even realize until they went to space and they came back and they realized, oh wow, the composites, is full of water. Well, because it's awful cold in space, you know. So there was a lot of new things that they had to do. And so even though like a lot of the like at Virgin, a lot of the aircraft is composite, but underneath all of that is a lot of aluminum, steel, on the inside. And so so a lot of times we didn't until we had a problem, we didn't know what to inspect for. So when it came back and we said, oh, wait a minute, we're starting to get these cracks here, but realize you had created an airplane, aircraft, right? The space shop that never existed before. And until you go to space, you don't know what forces it's going to be hit against. So you ended up noticing things are going wrong. Now, okay, all right. Somebody looked at something, didn't look right. We pulled it out and found out it's cracked. Okay, so now you got to create a technique for it. And so basically, you got to say, okay, this is what a good part looks like. We measure it and scan it. Nothing comes up. And then here we scan it. But then you also have to realize, too, if you don't hit something at the right angle, you may not catch it. So I think it's definitely in the space industry now. And as we know, like Blue Origin is really becoming a big player, and SpaceX, is already through the roof. They're probably going to have a lot of cases where I think the Eddy Current people need to probably contact them about doing a lot of stuff. Because when I was at Virgin, we had, I don't know if you're familiar with this machine called a bondoscope. And we had all kinds of problems with bondoscope. I don't know if it's you guys had the same thing, right? So there were some machines out there that we bought that we just never could ever get it to really work correctly. So when it comes to, like you said, how do you verify? You got to verify. You got to have a good reference standard, and then you got to find out exactly what we're looking for. Are we looking for longitudinal defects? Are we looking for defects that may be at an angle? Are we looking for erosion on the face of a piece of metal? So it all depends on what we're looking for. And then you got to compare it against what you know is perfect. This is a perfect part. This we know is serviceable. And then in another cases too, you got to decide what's no go and what's go. Because there's going to be some cases where they may be willing to live with some cracks on certain parts, Yeah. So it's a lot to it, based on my experience.
Yeah. Thanks, Mr. Ronnie. I think that's a good kind of explanation on the reference blocks and the reliance and the need for the clarity and trust on the Eddy Current testing course. Mr. Alexa, do you want to go ahead on your experience?
Oh yeah, mine is pretty simple actually all the years because first I think except for Meerbeek, Ronnie and I were the level 3s in NDT. Now level 3 means one of two things. You've been through rigorous training and experience system, and then you get certified and whatnot. Usually through experience or God willing, you are smart enough. The point being that you get to train people one way or the other on site in the classroom, and from that you learn a lot. My approach is very simple. So Middle East, Diraj, I'm sure you work in the Middle East, right, Diraj? You work in the Middle
I do.
Yeah.
Yeah.
So you were the Middle East about, like Ronnie was saying, standards. Out here is ISO. Now the classic one, the classic was BSEN 1711 for Eddy Current because I'm on impedance plane. I'm on impedance plane analysis. So classic, complex plane. BSEN 1711, and then fast tracked around 2015. It became 17643. That is based on ISO 15549 and then 15548 and 49. Now, what am I talking about here? Training and procedure. That's my approach. If the procedure is well crafted for the given application, or it is generic enough to be covered by 17643, good to go. That's number one, procedure. Number two, and very crucially, the inspector. So when I question the guy, I go straight for the physics because that's the mothership, physics.
Yeah.
I show him a simple inductance equation. If he can recognize the equation and tell me what that is, okay, now we're starting somewhere. Number two, probes. What's the difference between an absolute probe, bridge probe, reflection probe, bridge differential, and reflection differential? Because there's 5 common configurations, because they kind of mix it up a little bit. If he can tell me in common sense language what these three, like a layman could understand, then I know, okay, this guy's got good operating common sense. So he's got the basic knowledge and he has got good operating common sense. Now we're good to go. If these two things don't check, then whatever the results are, I cannot rely on them, basically, because that's the start of it. If he doesn't know about inductance and how it plays when inductance and primary current, how they're playing with each other, then he wouldn't understand probes, which means the machine itself will be more complicated because you talk about filters, high pass filters, low pass filters, depending what you're dealing with, multiplexing when it comes to, for example, pipes on support brackets. How do you isolate heat exchanger tubes? Now, I don't do a lot of work there, but I've done a lot of research there. Again, procedure and the physics. So if I can ascertain that the inspector, so for the company has got a good system in place, procedure is good, and the inspector has that good working knowledge, that's pretty much it. He normally shows that through a calibration, and calibration where, like on a sample, real defect component and how he goes about it. And so.
Yeah, that's a great thing.
That's
The
what
real
it is.
Yeah. The real validation always gives you the happiness. That's the main intent of doing the mockups and looking at the the signal patterns and stuff. It makes it more confidence and
But I'll just add briefly. If a guy does, I don't know, let's just say 10 jobs over a 6-month period for a given, like I say, a plant, and throughout you're only getting, and it's pretty much non-mag. So non-mag is pretty easy. Mag is tricky with the permeability, as you guys know, and he's getting constantly no findings, like literally.
Correct.
And the reports are not that, let's just say, not that clear. Let me be polite and say not clear, because reporting, as you know, if you go to ISO 15549, the requirements in there are quite detailed. See, so if the reporting is kind of sketchy and it's getting no findings at all, that's my first red flag right there.
Yeah. Great. Thanks a lot, Mr. Alexander. So I think it's going very interesting. And over to Mabik.
I just want to say what Alexander highlighted. Both things are crucial, of course, the procedure and the operator skills. But if the procedure is not in place, the good thing would be to follow some benchmark samples. So benchmark samples which validated by other types of NDT methods, so you can trust on the results. Also, another thing is cross-validation is the key. So if you are receiving the eddy current results, but it is showing some validation with other tools such as ultrasonic or visual methods, it might be a good also results to follow.
Yeah, perfect. Yeah, I think all of us.
They bring up something else that's a good point too. There is really a shortage of good reference standards in the field, probably all over the world. Trying to find good standards is really hard. And then even though, we make a lot of electronic ones, but trying to have a true replica is getting harder and harder. And then when you look at, like I said, in the space industry, oh man, they're really hurting for standards.
No, you won't be able. It's going to be difficult, guys, to find real flawed samples historically. Mostly you find them in training centers.
Yeah.
But to get one, like for example, I'm in underwater. Like Merrick just said, cross referencing, like validation. You try to validate underwater results, man. That one, you know what I mean? Yeah, you got to get an expensive ROV system. Put that thing down with. It's a whole. That's why I came back to that basic check of especially the physics, the inspector's knowledge of physics, because you'll be amazed at how some guy. I've seen guys who have been in the business, but he cannot recognize the equation for inductance. I'm serious.
Yep.
But he's got some experience. He knows how to different like check a box and whatnot and thing. But that's pretty dangerous. You know what I mean? So, yeah.
I think everyone nailed it on it. So reference validations and that kind gives clarity and trust on the job, the technician, everything overall, right? And as you guys have mentioned, that's my experience as well, getting the true flaws. And sometimes people just scrap the cracked specimens or something, but NDT person will probably know how valuable is it for future validations and stuff. I mean, that's a pain for, I think, across the world. I think it's going pretty interesting with deeper conversations. Let's just pace it up a bit to just leave some space for audience to have some questions. So rolling on to the next question, what are the common pitfalls we generally come across eddy current testing, like to kind of give some clarity, the top mistakes, let's say, eddy current technician tends to do, like in terms of lift off from coatings, awkward geometry, is he able to think what is it, a profile, other lift off signals, or like, let's say, setup calibration errors, poor documentation. Just, I think Alexander was talking about it just a while ago. But just to rephrase and give opportunity and bring it for the broader panel. So what are the common pitfalls or things, mistakes you see typically with eddy current testing, with especially the lift-off calibrations and so on? Yeah.
I think Alexander brought up a good thing about the probes. Are you using absolute? Are you using differential? Sometimes that's in a lot of cases where we probably should have used a differential when we use an absolute. So I feel that too. The proper probe for the job to look, like I said, it's all about what are you looking for. You got to decide, and sometimes they don't even know what they're looking for, right? Alexander probably I see shaking his head. Do you really know what we're looking for? So I do think the wrong probe is the root of a lot of the issues.
That's right. Quite simple. The probe.
Yeah.
Because there's this. So when it comes to probes, apart from configuration, basically winding and all that, there's now the parameters such as shielding versus unshielded, edge effects and things like this. Which one and why? You want to inspect ferritic materials, definitely unshielded. But the inspector is going to say, I'm looking for very small cracks. I need resolution. No, you need a good magnetic field sufficiently strong enough to overcome the primary, the primary magnetic field, because it's about the inductance. So you want to make sure your probe is unshielded because magnetic field is stronger. It's going to go in nice, and also lift off variable. The lift off variable is well, taken care of when you have an unshielded probe compared to. So probe all the way.
Yeah, I think that's a top one. Mr. Murphy, do you want to share your thoughts?
Basically, some of the top mistakes that I made, I dealt with the early prototype of the probe, of directional probe, early on my PhD journey. So I think the misconnecting cables was the primary kind of a challenge in the early stage, because you are having some bridge. Also, all of this kind of early prototype. If guys, when you're working with early prototype, there are many kind of device in order to connect all of them properly. Another was so I fixed it just by verifying the signal path using some oscilloscope or some multimeter. Second is juggling too many variables. At my early stage, I was very happy by surrounded some talented professors like Robert Hughes, Paul Wilcox from my university. So they helped me to move like one parameter only. So when you are, for example, fixing everything, every parameter, controlling them, and only moving one parameter, and you can see what this change associated with this parameter, So the third thing was mounting the probe components into the 3D printed or any type of housing, which can also remove some noise associated with vibration coming from the moved parts. This is also another kind of jungle. Also know your defects, I would say, the final one, because when you all of different type of defects behave with different signal shape. So interpreting these shapes, what type of mode you are using depends on this, and you need to also have this kind of understanding, as Alexander said, about the edge effect, lift off, many other parameters. It is like the snowball effect.
Yeah.
Mine, by the way, one of my classic rookie errors back then was I was using a 3D printed Absolute Probe, actually 3D printed actually with good graphite, graphite housing,
Mm,
and I needed as much field as possible going to the part. So I
mm,
took off the probe, the extra, the extra probe shield, if you like, this thing, the standoff. So I took off
Mm.
the normal, Scotch tape standoff to kind of, oh man, it was fairly smooth weld, but I learned the hard way. Yeah, that graphite thing is not. I mean, we know it's kind of soft, yeah, but it was really it wore off much faster. Started
mm,
sending my signals left and right, bro, left and it's pretty
that's it.
expensive
Great.
to replace that stuff and get 3D print. I thought it was cheaper, but it's quite expensive. So for me, that was a lesson learned. Always stand off. Maintain it, calibration and doing scanning
Yeah.
because the probes are expensive. Yeah.
That's a great point. Thank you. And I think we have discussed a lot about the calibration blocks, liftoffs, errors, how to do it, why eddy current. So let's say we do eddy current testing. It's always a nightmare for any technician or the technical manager or whoever, right, to convince the management. So to put it into a question for discussion, how do you turn your eddy current findings into clear actions like accept, reject limits? Who decides what gets recorded? How do you convince your auditors and make it comfortable? Like based on your experience, do you have like kind of a dashboard or a report line you insist on so that to follow for the people in audience to make their life easier to get the management consent?
Ronnie, you want to go first, or I will go first?
You can go ahead, Alexander. You can start this one off.
Well, simple, guys. Agreement, PO or contract agreement. What are you after? In our case, cracks. Very simple. Eddy current is mostly about cracks. Find
Yeah.
it. Then if you can afford ACFM, size it. Because that's the reason we go, especially underwater. So ACFM does the sizing. If you can afford it, it's pretty expensive. Eddy current
Mhm.
picks it up very quickly. Usually cracks. So as long as it's a crack signal and can be proven as such, basically amplitude and phase, correlation,
Yep.
especially amplitude, because of depth, we're looking at what, 0.5, so 0.5 mm to 1 mm to 2 mm. The plates we use offshore is different. We use 0.5, 3.25, and 6 mm deep and through plate. It's about 10
Mhm.
10 mm thick plate for surface calibration. So we calibrate on the surface, dive, stabilize it on any standard area on the actual 60-inch wide column underwater,
Yeah.
then go for the scanning.
Yeah.
So if the contract says no cracks allowed and you can prove it's a crack, done. Pretty simple.
Yeah.
It's not complicated because in our case that's what we did. We managed to find it by eddy current testing, and then we had the operational allowance to get the structure up above water. So every time when we did the one case, we found it by eddy current testing, and they did a very thorough cleaning at about 3,500 psi with a cavi blast gun, like almost what is called basically like you're getting about SR3. Now,
Mm.
no, sorry, SA3. SA3 means down to like almost machine finish, like very high polish on the metal. So we did that, and we could see a pinhole welding stage defect, like a pinhole through like. So we picked it up under the marine growth, and then we very thorough visual we found it. The other two cases picked up the signals, got it above water, cleaned up MPI cracks. So yeah, kind of validation over and over because the Sensima system that we use is quite good. The software is quite good actually. So yeah, so once you can prove that it's a crack for the client in the oil and gas business, that's it done.
Yeah.
Now they get to decide. Okay, do you want to keep it? Do you want to go for a future dockside repair, whatnot? So yeah, that's it for me.
Yeah. I think contract is pretty much valid one. Mr. Ronnie, yeah.
Okay, for me, and like I said, usually you have a criteria and it will say, hey, if it's more than an inch, 2 inch, and so on and so forth. And it's usually not hard to make them understand, hey, this is the criteria, this is the no-go, position. My biggest problem is, I'd say the two biggest fights I've ever had as far as eddy current goes, and y'all may think this is funny. Number one, I'm not a proponent of tracking cracks. I say we find it, we fix it. But a lot of places want you to track it. I'm not a proponent of that. I think if you found it and it's cracked, it's not gonna go away. Fix it. But there's a lot of cases where we're tracking cracks. Number two, the second, but no, that's probably the second biggest argument I've had. Number one is finding something that they told you that wasn't supposed to be there. When you inspect something and it's a crack in an area that is not supposed to be a crack, or you find something that is beside the inspection area, but it's not the inspection area. Y'all understand what I'm saying?
Yeah.
Those are the two biggest fights I've had in industry. Hey, what are you doing looking at that? I couldn't miss it. It's 4 inches long. It's a crack. Well, that's not the inspection area. And I'm telling you, I had some drag out fights with that. And then, like I said, I'm not a big believer in tracking cracks. I say we fix it.
That's a great thought. I totally agree on that. Mr.
But you're gonna
Mona.
come into that, right? You're gonna have to deal with that.
Yeah,
know?
right.
Well, you're gonna, in most cases, offshore, you got to track it, because to stop that operation, you're looking at the gas.
Yeah.
That thing is sitting on a gas line. That thing is going on 300, almost 300. And how many barrels? But I've forgotten the last figure in Qatar. There's no, if they stop, it's, you know what I'm talking about, operational politics.
Right.
Yeah.
But I'm just saying that that's something as an NDT Eddy Current guy, you're gonna understand. You got to deal with that. You got to accept their rationale for that.
My last client in Malaysia and Qatar, I sent a report to them giving recommendations after signals were found, to be proven and stuff like that. And they told me, your job is to inspect and give the report, don't give recommendations. I was like, okay, man, thanks. That's it. So
that's true.
Yeah.
Even though you still may not feel right about it, but that is the fact.
No,
okay.
But they're still going to want to take hold your company. Like in my experience, they're still going to find a way eventually. If something goes wrong, they say, don't track it, fix it. They're still going to find a way to turn back to whoever was the service provider. I've seen this a lot, because some manager sitting somewhere doesn't want to take responsibility. So yeah, I don't want to kill too much time. So yeah, guys, please.
Yeah, but just know that is an issue. That is an issue in the field. Right. Yeah. Tracking and finding something ain't supposed to be in an area that's closed was not exactly the inspection area.
Mr. Babik, do you want to add your thoughts?
Yeah, I would just simply add maybe some international recognized standards as ASTM A243, and also the ISO 15548. These standards provide some clear guidance, so they guide us what gets recorded and who signs off, all of this stuff.
Yeah.
Also, a clear inspection report should be in place, for example, with probe settings, with defect location and the decision rationale. So these kind of things, I think, is something reported early on, so we can trust on it there.
Yeah. Thanks, Mr. Mabik. So I think with one closing question to give clarity for all the audience, to leave, let's say, everyone with clarity, to take back all the discussions we had, the difficulties, advantages, limitations, management, right? We had a lot of discussions. If, let's say, at your site of work, you want to improve safety of Eddy Current testing in the next, let's say, 12 months or so, right? What is the one thing you want to start with, the one thing you want to stop, and one metric to measure to really, see whether Eddy Current testing is going the right track? Who wants to go first?
No. Okay. Ronnie?
I mean, as far as, like I said, to me, I feel that a lot of things should fall on the level 3s, as far as, always making sure that everything's done safety, and always try to be a continuous improvement model. Can we do this better? Can we do it, more economical? And definitely safety should, number one, be the priority. And everything we do should be safe. And I've seen cases too where, like we talked about earlier, about not having the right probe can sometimes, trying to get in there and rearrange your body to get on something, have created some issues. And so I do think we definitely need to have more focus on getting the proper probes for the job. And it may not seem like a big thing, but if you're scanning the area and you're fully extended, believe me, my rotator cuff is about done. I've done a lot of those inspections like that. Because sometimes you got to get on it. You got to get the right angle on it. You got to be able to maintain that surface contact. And sometimes it can have an effect on your shoulder, and your wrist, and things like that. But I do think that, to me, the level 3s should always be trying to find ways to make sure it's safer. And then another thing about, I think a lot of people don't understand too, about when they hire a level 3, is that you got to make sure you got a level 3 that can communicate to people. Because a lot of this stuff is over people's heads, or they think it is. You know what I'm saying? So you get a level 3, because I never understood, like I met level 3s that were just not people person. I'm like, why is that guy level 3? He acts like he hates his job, or he doesn't really relate to his text. You know what I'm saying? Like, I just never understood that. So I think when you do a level 3 is more than just someone that knows all the theory of Eddy Current. He's got to be a good communicator as well. And he's got to be proactive in a lot of things, you know? And I think that makes a big difference in the field, with all due respect.
Yeah.
Yep,
Alexander.
totally agree. Yeah. Yeah, for me, if I understand the question correctly, there's so two parts there: safety and i.e. determining if Eddy current is going right, basically, and maintaining the such, so safety aspect. For onshore work, in my experience, nothing more than just sticking to the standard above water safety measures, H2S and all that stuff, and fire safety whatnot. So that's done. Now, underwater is a tricky one. ROV systems comes with a lot of cables, a lot of tether lines. That the amount of piping stuff involved is quite significant, especially when you're doing more than 100 meters deep, such as platforms. Southeast Asia looking more than 500 meters. So and there are two kinds of ROVs: what I call the operator, highly maneuverable type, where it's complete operator skill, like remotely, maneuvering it and whatnot. And then the ones that are semi-automated. We call them world-class ROVs. They're more expensive, of course. From a safety perspective, the world-class ROV comes with a lot more kit that can make the overall job in terms of getting down there, getting stuff done, recovering your machine and all the tools and whatnot. And they've got the right rigging in place from the rig cranes and whatnot to get that done. So world-class ROV by all means. The smaller ROVs are more cheaper in terms of the contract arrangement, the contract arrangement and whatnot, but it requires a lot of manual labor also involved, moving stuff left and right and things like this. So the safety, the RA, risk assessment, needs to be quite rigorous in terms of what could happen to personnel if you don't account for certain aspects. And we're dealing with more than 3,500 psi. Let's say low end 1,500 psi to 3,500 psi. Now that's a lot of pressure. If anybody and it's heavy gun, that thing could put a hole through a human being right straight through, So they've had situations whereby on board the bypass valve was accidentally left semi-open. So when the operator is electronically controlled, so when he went on, it's a relay which activates both the water pump system and the ROV navigation system, basically the thrusters and whatnot. So that thing went whoop. Fortunately, there was ROV systems, the RA needs to be quite detailed, so taking care of that. For personnel, so in terms of so to the second part of the question, making sure that Eddy current is quite fit for purpose, if I understand it correctly. And well, what I'll say there is, as long as the procedure, for me, I use 15549, the generic like global Eddy current standard, to be a good benchmark. As long as the procedure is properly done and validated for each specific application, then you can pretty much count on it, because in that process, you will determine the very critical variable of inspector competence.
Yeah.
Then from there, the rest is basically, there's nothing to, and like Ronnie said, level 3s. Yeah, you don't want to be this, I don't know, management type guy who is, I know my stuff and I'm either, on a high horse, or I know my stuff and I can't really relate or connect or, pass on knowledge. You want to simplify knowledge. You want to make sure that, the people can take this, you can take this complex thing and give it to them, quite easily. So the level 3s here, they've got a lot of work to do in that area as far as Eddy current is concerned. In fact, as far as electromagnetics is concerned, MFL, ACFM, RFT, and of course Eddy current testing. So that's it from me.
Great. Thanks for that, Alexander. And Sumavik, do you want to add some closing comments on what you want to start and measure?
Yes, I think start by placing some good procedures to follow. So this is, I think, particularly important for such experts like Alexander or Ronnie, because we will left this world, but our procedures will help to increase improve the repeatability of others' work. Maybe they will use the same system, the same probe. And another thing is stop rushing into measurements without a stable setup, which is mostly said by my supervisors. And because this is help to get rid of some of your personal, I think, things. For example, if you are not relying on the theory or some previous kind of investigation, and you are not going after the right direction, And the final thing is, I think, to measure, I think there should be some metrics that you can trust on. For example, some signal to noise ratio, for example, because if you are only measuring the signal, let's say the voltage and trusting on it, but your noise level is also background noise from the non-defective part is also kind of a high. So these kind of things might be helpful. Yeah.
Yeah, that's great. Again, adding steps to the procedure to ensure that we have the right measuring tools. Perfect. I think it's a great concluding question, and I think we discussed quite a lot. It's quite heavy topic, and thanks for all of you to kind of digested it in a nice way with different perspective. I heard like from all the way from aerospace, subsea, rails. It was like holistic. I think it's a great discussion, and I think we have a question from audience. So let's take some questions. So Mr. Shankar is asking to suggest some of the books for basics of Eddy Current, probably to someone to start with, right? Do you recommend any books or kind of any material?
Yeah, that's quite a rich one, actually. I'm holding up one right here. Anybody was, I don't know, my screen can make, you can see that. It's on ASNT, basically. My resolution
Right.
quite good. I think it's kind of poor. You can see that. My resolution is bad, I think. Can I? My camera is not too good. I don't think my camera is good. Anyway, this is Fundamentals of Eddy Current Testing by Donald J. Hegemeyer. It's a very fundamental one. It's on ASNT website and whatnot. So ASNT has got some pretty good content. So they've got some really good content on there, Most people who even prepare for the ISO 9712 system, they use ASNT material a lot because it's simplified. It's very, you can easily, for those who want to do just the fundamentals, you don't want to go too deep. I'm a physicist by education. I'm sure same with Merbek and Ronnie. So I'm a physicist and mathematician. So for me, it's kind of intuitive. I can easily relate to it and whatnot. But most of I found since some very smart guys, but they just need to, overcome that little physics barrier, basic calculus and algebra, and understanding the equations, and then from there it's a runaway train. So yeah, books like from ASNT stuff like that, yeah, was definitely a huge plus, and it's pretty small, also small and easy to read, yeah, and also affordable, $47 basically.
Thank you, Alexander. Ronnie or Mabik, do you want to give some recommendations?
Okay. By the way, and Ronnie's paper and Merbek's paper also, the paper, his paper, I read it.
That's it.
I think from my side. Yeah, sorry.
Yeah, there's a lot of good books and things out there. A lot of and a lot of the premier NDT companies, a lot of them have things on their website. And of course, we know ASNT is definitely a good resource in many cases. Yeah. One of my biggest things is that I think a lot of times especially when you're a younger tech, you need to network more. You need to find people in the field that you can kind of link yourself to. And then another big thing, I'm going to tell you a quick thing that happened to me. I was working with a major aircraft manufacturer, and I had an inspection that we were measuring the windshield. Now, this is like a brand new aircraft, brand new, big time passenger jet. And I could not get a reading. And I tried everything. So I called 3 other plants and I said, hey, can y'all go out there if you got a so-and-so aircraft out there and see if you can get a reading on this windscreen? And they said, hey, we tried it for an hour. We couldn't get a reading. Called another plant. So I called like 4 different places and nobody could get a reading. Ended up getting with engineering. Come to find out this was a special type of windshield and you couldn't get a UT signal on it. But the problem was 30 of these inspections have been signed off. Why? So I say, don't be afraid if something's not working right to call somebody and say, hey, are you having this problem too? You might uncover something that everybody's having a problem with. But I think sometimes we don't, use each other in the field enough and communicate enough, And that was, so who knows what else people are doing, thinking it's not that big of a deal, it's just the windscreen. But it's about integrity. You're signing your name to something you didn't do,
Fortunately.
So everybody had to come we had a big meeting, like, okay, how many of y'all did this inspection? Everybody was quiet now. Ain't nobody got nothing to say,
Yeah.
But I'm just saying, just call and confirm it with another tech, send us down the road to find out that something wasn't right. So don't be afraid to talk to fellow techs in the field, especially people that's experienced, and always maintain your integrity, even if it's just something simple.
Yeah.
I
Totally
think
agree. Yeah.
I think one classical book is a good reference. It is Nicola Bowler's book, Eddy Current Non-Destructive Evaluation, which was helpful for my first year of education. Yeah.
Great recommendation. Thank you, Mr. Mervin. And I think Daniel has just commented on Ronnie's point. I totally second it. Showing up the ASNT local chapters, having the network around yourself wherever you are there, having a global network, right? It really mattered to me as well. It was in the recent ASNT event in Orlando. I think the amount of knowledge you have with the people around you in NDT community is a lot. And unfortunately, I feel probably people are having more knowledge than the books. And I think it's slowly changing with more books coming up, people publishing and so on. But as you said, Ronnie and Lex, I think, yeah, people are very important, and we should surely, stick to the basic standards, ASME, ASTM, and all those stuff. But ask for doubts, ask for help when it is needed with the local communities and the ASNT sections. Yeah, that's great conclusion. I think we don't have any other questions in the chat. So probably I'll pass it on to Katie. Over to you.
What a powerful and insightful discussion that was. A big thank you to all our panelists, Mr. Alexander Mirbek and Dr. Ronnie, for sharing diverse perspectives from field application to research and training excellence. And of course, a special thanks to our moderator, Dheeraj, for steering this conversation with such depth and clarity. So today's discussion truly highlighted how Eddy Current testing continues to evolve not just as a technique but as a safety enabler for industries working under high risk conditions. So, before we close, one last reminder, don't miss our Robotics for Confined Space Inspection Buyer's Guide 2025. It's packed with expert advice and practical frameworks to help inspection teams choose robotic technologies that enhances safety and efficiency. You can download it anytime at onestopndt.com. And thank you all for tuning in and being a part of NDT Talks community. It was really great having you all. Until next time, stay safe, stay curious, and keep pushing the boundaries of inspection